Welcome back, dear students, to the tetrahedron chemistry classes. So guys, in today's lecture, which is my lecture number 3, I am going to start the another part in the types of polymerizations. And in the earlier lectures I have covered the things in the pretty much details. Let us just recapitulate what we have done so far. So I am going back to explain, or to show, not explain, to show all the slides what we have done so far. And if you are new here and watching video for the first time, right, so what you can do, you can first learn the things from my earlier videos as well. I am giving you the link in the description box. So this was my first slide of the first lecture, where I have classified the different types of the polymers depending on their use in the daily life, right? And then I have given you the details classification based on the different types of the things which are necessary to classify the particular kinds of the polymers. I will not discuss these things again and again. Okay, this I have already done. And then the terminology used in the polymer science, I have used these things as well. And then functionality concept, right? And then your types of polymerization, and the type of polymerization, the mechanism of addition polymerization, I have done free radical polymerization, right? And then after free radical, I have done the cationic polymerization, and then I have done your anionic addition polymerization as well. And in the today's lecture, I am going to discuss the another very important method of polymerization, which is the condensation polymerization, and this is my lecture number 3. Please remember. And condensation polymerization means there step growth polymerization. That means you will not form your polymer in the earlier stages of the polymerization reaction, and stepwise you will grow your polymer, and at the end of the reaction, or only in the later stages, you will get the polymer. Condensation reactions, you know what are the condensation reactions, where the two reactants reacts together and they eliminate the small molecules, and the two molecules actually join together. It is not addition, it is the condensation. We will condense the two reactants and the small molecules. What is the definition of the condensation reactions? Molecules join together with the liberation of the small molecules like water, ammonia, ethanol, etc. like this. Okay, so what happens in the condensation polymerization? In step growth or the condensation polymerization, the polymer build-up process through a reaction between the functional groups of the monomers. Since functional groups of the monomers are reacting, that means your monomers must be bifunctional in that case, at least bifunctional, if not less then, right? If not less. Since these functional groups are reacting together to form the polymer, there is no need of the initiator. But in the earlier case, in the addition polymerization, we need the initiators. That's why based on the initiators, we have the cationic, free radical, and the anionic polymerization mechanism. Okay, so these functional groups can react together to form the polymers. So this is stepwise buildup of the polymer. What is the meaning of the stepwise buildup of the polymer? First of all, you will take the monomers, and your monomers will combine to give you the dimer, and then dimer will give you the trimer, and then the process goes on, and you will get the oligomer. And when this process repeats, the formation of the oligomer, and after that the process repeats of the n times, right, then you will get the polymer. So what happens, you see, you have this particular A2 type of the polymer. Of course, it is bifunctional, right? Monomer, it is the bifunctional, and this BB monomer is also the bifunctional, and these two combine to give you the dimer. See, since this is the general representation of the reaction, so I didn't show you the elimination of the small molecules, but in the real examples where we will form the condensation polymers, I will show you the liberation of the molecules as well. Okay, now you form this dimer, and then your dimer will react with this A2 type of the monomer. It can form a trimer, and similarly this dimer can also react with the BB type of the monomer to form the trimer, again different type of the trimer, and this series actually goes on and on. And when it repeats n times, then you will end up with the polymer. Please remember, it is very, very important. So they all react together to form the tetramer, pentamer, hexamer, heptamer. If we stop the reaction, we end up with the oligomer, but not the polymer. polymers will form in the later stages in the condensation polymerization. This thing is different. This thing is different from the addition polymerization, because in the addition polymerization, in the initial stages you get your polymer, but in this condensation polymerization you will get the polymer in the later stages. If you stop the reaction in the earlier stages, in the shorter period of time, you will end up with the oligomer. And I already told you how we can differentiate between the polymer and the oligomer, right? The way is like that. See, you have, say for example, you have prepared certain polymer and you are not sure whether you end up with the oligomer or the polymer. What you can do, whatever the product you have formed, you can add or remove 20 to 30 another monomeric unit to that product. If the properties of that product does not change, that means you end up with the polymer. If the properties, that means removal or the addition of the monomeric units, 20 to 30 monomeric units, right? If the removal of them changes the properties of that product, that means you end up with the oligomer. This is how you can differentiate between the two, right? And you see, the ideal degree of polymerization in the step growth polymerization depends on the specific application and the desired properties of the polymer. Since you are forming the polymer in the later stages of the reaction, that means you need to know what kind of, or what actually degree of polymerization you require. So degree of polymerization you require for the special or the different kind of the purposes is different, right? So typical ranges of degree of polymerization for the condensation polymerization, say for example, if you are preparing nylon or the polyesters, then 100 to these are the fibers, nylon and polyester, you know, these are the fibers, and for these fibers actually you need maximum of 500 degree of polymerization. You don't want to go further. So that means somewhere around your 90% or something, 90% conversion or 90% completion of the reaction will end up with this particular reaction. In the little while we will see all the things with the help of the numerical as well, right? And if you want the plastics, right, your application requires the plastics like your polycarbonates and polyurethanes, right? So this 3 is actually the error, right? Please ignore this one. Okay, then you need 50 to 20 degree of polymerization. That means again you can stop your reaction somewhere around 80% of the completions. Okay, right? And if you need these things for the coatings, like see, this is the Diwali season which is going on, and we all generally, especially in the North India, we clean our houses and coat our walls of our houses with the paint, right? So when you use this coating things, right? So for coatings only 10 to 50 degree of polymerization is required, where epoxy resins, polyurethanes, all these things are there. So 4 and 5 you can ignore. Actually these are the bullets of these actually numbering, right? These don't have any meaning for 3, 4 and 5 here. But for adhesives, right, say for example epoxy resins you are having, and then you are not here your epoxy paints, in the earlier case point number 3 epoxy paints, and in that case epoxy resins, right, where you use this epoxy as the adhesives, or you see cyanoacrylate, you need very little of degree of polymerization, that is 5 to 20. That means you can stop your reaction up to 70% of the completions. Okay, but if you need the high performance material, then you need very high degree of polymerization, somewhere around 2000 dp, right, especially in the aerospace, automotive, right, and your heavy vehicles, right, earth moving objects, where in that cases you will require if you require these heavy high performance material in those cases, like your Pokeland and say your tank, right? Here if you require high performance material, then you need to do the reaction to the very high extent, like 99.9%, 99.8%. Only then you will get the polymers which would be your usable polymers. Okay, I hope this is quite clear to you. Now moving further, you can see here, now see, calculate the dp, that is degree of polymerization of an equimolar mixture of the hexamethylene diamine and adipic acid. So hexamethylene and adipic acid, for the percentage conversion, this is percentage conversion, that is extent of the reaction of 50%, 80%, 90%, 95%, 97, 99, 99.5. 99.7 and 99.9%, right? We'll see this thing with the help of the numerical. So to solve such questions, you need to know some of the important formula of your polymer chemistry, and one such very important, the great formula is the Carothers equations. So I'm writing Carothers equation. Okay, and what is the Carothers equation? It is quite simple. Carothers equations is your dP, that is degree of polymerization. Okay, and that degree of polymerization equals to 1 over 1 minus P, where P is the conversion. Please remember, P is the conversion in percent. Okay, if you use this particular formula, then you can very easily calculate the degree of polymerization. Let's take an example. Say for example, you are calculating the degree of polymerization when your conversion is say 50%. Okay, so you will write 1 over 1 minus 50% means 0.5, right? 50% basically is what? If you write the 50%, basically it is 50 by 100. Okay, that is 0.5. That is the value of the P conversion, right? So if you solve this, then you will get the degree of polymerization 2. Similarly, if you have the degree of polymerization little bit higher, say your 80%, right? So that is 0.8. For 80%, it would come around somewhere around 5. Degree of polymerization 5. If you keep on calculating your degree of polymerizations using this Carothers equation, then you will end up with this result. So I have already, because this is the simplest formula, I don't want to include the most of the calculations here. So I have explained with the help of 1 or 2 examples. Now it is up to you how to calculate degree of polymerization for the different rates of the conversion. So this is P, 50, 80, 90, 95, 97, 99, 99.5, 99.7 and 99.9 conversions. And accordingly, you, with the help of the Carothers equation, you are getting your degree of polymerization of 2, 5, 10, 20, 33.3, 100, 200, 33, 333.3 and 1000 degree of polymerization when your conversion is almost 99.9%. So you know, when your degree of polymerization is your between 1000 to 2000, your high performance materials are there, especially in the aerospaces. You have seen this in the earlier slide. So if you want to form this one, that means you need to conversion of 99.9%. For fibers, it would be good if you stop your reaction at 99.7%. And for plastics, basically you can go up to from 99 to 99%, right? And for coatings, this percentage is the 97%. And you see, for adhesives it is here 95%. So earlier I said that you can stop your reaction at 70% and 80%. So when you stop your reaction say at 50%, you get 2, right? At 80% you are getting 5, and even at 90% you are getting the 10 of your 10 degree of polymerization. And what is the application of this 10 degree of polymerization? Let us quickly check. So 10 degree of polymerization, you see, it is only used in the coatings here, right? You can see I have shown you coatings is written here 10 to 50. So you see, depending on the different kinds of the application, you decide your degree of polymerization. Okay, this is how the things goes, and it is very, very important for you. So guys, now you have seen how actually the degree of polymerization is directly related to the percentage conversion. Higher the percentage conversion, higher would be the degree of polymerization. Now let us compare the degree of conversion and the molecular weight of the polymer in the two different methods of the polymerization. First was your chain polymerization, or your chain growth, or your the addition polymerization, and your second is the step growth or the condensation polymerization. First see this blue or this green color plot, right? And in this plot you can see here in the very early stages you are starting to get your high molecular weight polymer in the chain growth or the addition polymerization. See, if you extend this line onto the x-axis, then somewhere around your say your 10%, right, or 10% or up to 5% of the completion of the reaction, you get your high molecular weight polymer reaction. And if you come here somewhere around say your 30% completion of the reaction. When your conversion is here at 30%, you actually get the very high molecular weight polymer. And after this, if you keep doing your reaction, then what will happen? There will be no change in the molecular weight of the polymer, but the yield of the polymer will increase. This is what happens in case of the addition or the chain growth polymerization. But what happens in case of your very important condensation or the step growth polymerization? You can see this molecular weight actually is not increasing in the initial stages of the conversion, not initial, but up to see when you have completed your reaction up to 80%, then your molecular weight of the polymer is very, very low, as you can see on this particular y-axis. But if you keep doing this particular reaction and you reach up to somewhere around here 95% completion of the reaction, that means conversion of the 95%, only then you will start getting your high molecular weight polymer. So this is the main difference in the two processes. First process, in the initial stages, you will get the high molecular weight polymer, and if you keep on doing the reaction, then you will get the higher yield of the polymer. But in the second one, the step growth or the condensation polymerization, you will get the usable or high molecular weight polymer only in the later stages of the polymer. This is the main difference between the two, especially after 98% conversion, which I have written here as well. Usable polymers in the step growth polymerization mechanism would be formed greater than 19% of the conversion. That means in the initial stages of chain growth or the addition polymerization, here this one, right, you are all monomers actually gets converted into the polymer. Here again, your monomers get disappeared in the reaction in the step growth polymerization, but you won't get your you will not get your polymer. You will get your trimer, tetramer, and oligomer like of thing. This plot is very, very important to understand. Okay. Now see, this is the general example of the reaction. As you can see here, there would be, say, these are the two polymers, condensation polymers. First is the polyurethane, and second one is the dacron or the terylene, and this is the reaction which is going on. So to explain the things in the little bit more clearer manner, I should draw the lone pair of the oxygen atom here, as well as lone pair of the oxygen atom here. Now how the reaction is going on, it is very important. See, the lone pair on the oxygen atom is attacking on the carbonyl carbon, right? And here this double bond between the carbon and nitrogen gets shifted onto this particular nitrogen atom. So nitrogen will get the negative charge and carbon will get the positive charge. This negative charge of the nitrogen will grab the hydrogen, and this will become NH here and single bond carbon. So this is NH single bond carbon. Okay. Of course, your double bond oxygen would also be there, right? See, there is a little mistake here. Okay. There should be the completion of the valency as well. Okay. So this how we can correct it? Because I have taken this particular diagram from certain book. This is basically your oxygen, right? And this is your carbon. Please remember, this is your carbon. So this is the mistake. And please be careful when you read the local publication books. These errors are generally you will encounter there. So that's why it is very important to open your mind while reading reading the books. Not only local publications, sometimes in the very high publication you may find this typographical error as well. So this is not the error done by the author, it is the printing error or typographical error you can see here. Okay. So here you can see this is this N is getting H here, so this has become NH. Okay. So this is NH, and then you can see it is connected with that particular oxygen. So this oxygen is here, and that carbon double bond oxygen, and that remaining part RO will come here. Okay. So this end is free now, and of course your one water molecule will remove from here. So how you can remove the water molecule? So I haven't written the water molecule, but I am writing that water molecule here. Plus H2 I am writing here. Right, plus H2O. So water molecule has been removed from here. Please remember, this is very, very important to understand. And the same thing is also happening here as well. This lone pair is attacking on this particular carbon, and this bond is shifting here. This is grabbing this hydrogen here, becoming NH, and now this is C double bond O and ORO, right? So if you want, then you can shift. Basically, this connection is in between your carbon and nitrogen. So this oxygen should be on the opposite direction. So this is again, this is error. This carbonyl should be here. Okay. But when I'll discuss the synthesis of this polyurethane, then I'll correct this thing here. And you can do, see what you can do, you can write that particular fraction, this particular fraction here as well. Okay, C double bond OOROR. So let me correct it for you. However, it would be very difficult to delete this because this is the scanned part or the scanned copy. But with the blue pen, I am doing this, right? So this would be your carbon double bond oxygen, and this won't be there, and this would be your oxygen, right? Like that. Okay. And then the things will go on, so, right? And similarly, this thing also happening here. You are having this particular diacid which is reacting with the diol to producing with the dechrone as well. Okay, so you can see here, see earlier, in the earlier way you can think in that manner as well. If you don't know what are the basics organic reactions, then you may confuse this reaction with the addition reaction, but this is not the addition reaction because water molecules are removing from here. Okay, so these are the condensation polymer, please remember, right? So the above two reactions actually are the condensation polymers. Now let us quickly see the difference between the chain growth polymerization, that is addition, and the step growth polymerization or the condensation, because it is very, very important, and in the examination, end semester examination, these questions generally asked, right? The examiner asks generally this particular question. So in the addition or the chain growth polymerization, it takes place only in the monomers having the multiple bond. You know, carbon double bond carbon, and see basically your vinyl family. Your vinyl family will produce the vinyl family polymers would be produced by the addition polymerization. That means carbon double bond carbon should be there or carbon triple bond carbon should be there. But in the step growth or the condensation polymerization, you need the monomer which have the active functional groups. As you have seen earlier, your diol I was using, right? And the concentration of the monomer decreases steadily throughout the reaction. So initially, see, is the reaction concentration of the monomer in case of the addition polymerization decreases steadily in the reaction. However, you get the polymer in the initial stages, but monomers would be there in that case. Earlier, I think I said that your monomers will be disappeared in this addition polymerization as well. This is not like that. In the addition polymerization, you get the polymer, high molecular weight polymer in the initial stages, but the monomer would be there, and these monomers actually goes on decreasing if you continue the reaction, and this will increase the yield of the polymer as well. Please remember, this is something very, very important. You need to understand, right? And then you can see here in this condensation polymerization, your monomers disappears early in the reaction, and you will not get any monomer, but you get the dimer, trimer, and the oligomer type of the things, but you will get the polymer in the later stages only. The point 3, it takes place without the elimination of the molecule. Definitely the addition reaction, in the addition reaction there would be no elimination of any molecules, but in the in your say condensation polymerization, your small molecules like water, ammonia, HCl, methanol, depending on the type of the reaction, they would be eliminated in the reaction. And in the addition polymerization, longer reaction time gives the high yield of the polymer, but the molecular weight does not change. But in the condensation polymerization, long reaction time are essential to obtain the high molecular weight of the polymer. Very important. Thermoplastics are generally obtained by the addition polymerizations, but the condensation polymerization can form the thermoplastic as well as the thermosetting plastics. Okay, what is the difference between the thermosetting and the thermoplastic? Right, thermoplastics are those plastics which on application of the temperature can be remolded again and again, but this is not true for the thermosetting plastics. I will discuss all these things in the later stages of the lecture as well, right? And point number 7, predominantly carbon is present in the backbone of the polymer. Of course, when it is the vinyl family type of the thing, then your backbone of the carbon would be backbone of the polymer would be carbon only. Would be composed of the carbon only, but in the condensation polymerization, heteroatom will be there in the backbone of the polymer, as you have seen in the last slide here, right? This particular, not last, but this one. You see, this heteroatom is present oxygen. Similarly, this heteroatom is present on the oxygen, right? This happens in the condensation polymerization generally, but not strictly. Please remember, last thing is shorter reaction time is sufficient to get the high molecular weight polymers. Polyethylene P, polypropylene PP, PEN, polyacrylonitrile PAN, PEN, polyacetate PA, right, and PVC, polyvinyl chloride. All these can be prepared by the addition polymerization. And in the condensation polymerization, long reaction time is needed. Example, epoxy resins, right? Epoxy coatings, your bakelite and resins can be prepared by this particular step growth polymerization. So this is all about the condensation polymerization and the difference between the chain and the condensation addition and the condensation polymerization. Okay. In the next class, I will continue with the other lecture, maybe the elastomers, right? Type of the elastomers, synthesis of the rubbers as well. Okay. So I hope you understood the lecture. If you like the lecture, please please give the thumbs up to the lecture and do share with your friends as well. And if you are new here watching video for the first time, please subscribe the tetrahedron chemistry class. I'll meet you in the next class.